Alright, welcome to Chapter 20. This is the last chapter of the semester, and it is not going to be too difficult, I don't think. We're going to be talking about the many different kinds of organic molecules you can build by snapping functional groups onto your basic alkane backbone. Most of this stuff should be fairly familiar to you. We're just going to cover it in a little bit more detail. We're going to talk about the different chemistry of these things. Organic chemistry is often called modular, in the sense that you can take the same molecule and snap bits off, snap bits on. Think of it like buying a car. You can get a car with absolutely no frills, or you can get one with all the bells and whistles, or you can get one anywhere in between, with or without heated seats, with or without the rear view camera, with or without the left turn signal. Organic chemistry is similar in that you can take the same carbon backbone and pop a bit on, pop a bit off. Or you could have a different carbon backbone with similar functional groups. You can modify these things in all sorts of ways. What we're going to be talking about is more how each of the individual functional groups will affect the chemistry of the molecules we're looking at. Alright, the simplest possible organic molecule is an alkane, CnH2n plus 2. It's just a carbon chain, a carbon backbone, with nothing but hydrogens on it, completely saturated, as it's called. This is the foundation of organic chemistry. All organic molecules are built on these carbon chains. All alkanes are nonpolar. Carbon and hydrogen are very, very similar in their electronegativity. They're not exactly the same, but they're fairly close. So the polarity of that bond is low enough that you can think of it as nonpolar. More importantly, every carbon atom sees pretty much a nonpolar environment within the molecule. And the molecule as a whole, even if it's a long, wiggly, wobbly, flowery chain with lots of branches or not, it's largely symmetrical anywhere you look within that thing. So it's going to be nonpolar in and of itself. Alkanes, their melting and boiling points can be quite variable, but that's based on two things. The size of the molecule and the branching of the molecule. So really small alkanes have very low melting points, like negative 100 or similar. As they get larger, the London dispersion forces, the intermolecular forces, get larger and larger as well, just because they have more electrons floating around. You also get what's known as the spaghetti effect. The chains can get tangled in one another, which is not something that will happen with a CO2 molecule or a water molecule. They're just too small. The other thing is branching. That's when you have lots of side chains coming off of your main chain. So a long flippity-floppity chain with the same chemical formula as a very highly branched chain. The floppity chain is going to have a higher melting and boiling point than the branched chain. This is because a lot of the branched chain can be thought of as sort of the interior of the molecule. With larger organic molecules, you can think of them as having an inside and an outside. Stuff on the inside, where the branching happens, isn't going to be able to have as much of effects on other molecules as the stuff over at the end of the chain, which can be thought of as being on the outside. So the highly branched molecules just have lower London dispersion forces, so they have lower melting points and boiling points than your unbranched chains. Next up, these molecules are pretty darn stable. You kind of have to beat the crap out of them to get them to react. You have to expose them to high energy light. They don't just react at the drop of a hat. So if you wanted to, say, add a chlorine molecule, to make a haloalkane, you would have to expose it to ultraviolet radiation, high energy light, or you have to expose it to a significant amount of heat in order to get them to combust. You have to provide a spark, that is, or a lot of match, something like that. Now, when it comes to natural compounds, biological stuff, alkanes are incredibly common. They are, the building block of life. So you will see these things everywhere. Next up, we have the alkenes. Your alkenes are alkanes with double bonds. Each double bond, that's the M in the above formula, represents 1 unit of unsaturation. So an alkane, with nothing but single bonds, is fully saturated. It has the maximum possible number of hydrogens. Unsaturation means removing some of those hydrogens. So in order to make a double bond, you have to remove a pair of hydrogens. Alkenes are still nonpolar. They still have low melting and boiling points. They're very similar to alkanes in that respect. They are a little bit different from alkanes in a couple of ways. The double bond makes the structure less floppity. They're less flexible. A double bond sort of locks it down. Single bonds are free to bend and rotate. Double bonds don't bend quite so much, and they are not free to rotate. So an alkene has a more rigid structure than an alkane. They are also a little bit less stable than alkanes. They're a little bit more reactive. They're still not hugely reactive, but they're a little bit more reactive than alkanes. And double bonds in your organic molecules are still quite common in nature. And finally, we have the alkynes. Finally, with respect to talking about multiple bonds. Alkynes are your alkanes, but with triple bonds. Each triple bond is 2 units of unsaturation. You have to remove 4 hydrogen atoms in order to get an alkyne, in order to get a triple bond on there. They are, again, fairly similar to your alkanes and your alkenes in that they're nonpolar, and they tend to have low melting and boiling points. No big surprises there. Changing the bonds, double and triple and so on, doesn't really change the nature of the organic molecule in that way. It does make them far more reactive. They're far less stable, is another way to put it. They much more want to get rid of those triple bonds. Triple bonds are not unheard of in nature, but they are quite rare. You get a lot of double bonds, you get a lot of single bonds. You don't get all that many alkynes when it comes to biological molecules. Not impossible, just rare. And rounding out the nature of the bonds, we have our cyclic alkanes, our rings. These are very common in nature. Rings show up all over the place. Every ring represents 1 unit of unsaturation. You have to remove 1 pair of hydrogen atoms. This time you're removing 1 hydrogen atom from either end of the chain, and then you're linking the 2 ends of the chain together, and that's how you get your ring. Cyclic alkanes, absent any other modification, they are still nonpolar. They still have low melting and boiling points. They're going to have a higher melting and boiling point than linear alkanes of the same size, but not a huge difference. And they are still going to have a nice low reactivity. Still flammable, but not as toxic or carcinogenic as other compounds out there. And the last of the unsubstituted alkanes, we have the aromatic hydrocarbons. The technical definition is that these are cyclic planar hydrocarbons with alternating single and double bonds. That is to say, we're talking about benzene and benzene-like things. As you can see from this, you have resonance in these things. Up here in the upper left quadrant, we have benzene, alternating single and double bonds. There's no reason for the bonds to be, say, 1, 3, and 5 instead of 2, 4, and 6. So they're both. and thus we tend to draw them as a six-membered ring with a circle in the middle. The benzene derivatives, or the polyaromatic hydrocarbons, the polycyclic aromatic hydrocarbons, are when you get multiple rings interlinked with one another like this. And they can get very complex and very big. But the aromatic hydrocarbons and the polycyclic aromatic hydrocarbons, they are sort of an interesting group. They are, the subject of their own branch of study, more or less. When it comes to whether they exist in nature, they do. Not so much in biology, but they show up in geology. They show up due to the formation of fossil fuels. In human environments, they show up as a byproduct, I should say, of combustion. Whenever you get incomplete combustion, you're going to get these polycyclics, and just benzene itself and so on. So they show up in smog and soot. They show up at barbecues. So they are basically a form of pollution in that way. They're quite stable, but they can also be carcinogens. We tend not to like them in our food and drink, but we can make use of them so long as we lock them down and don't eat or drink them. They show up in artificial detergents and things like that. And before we finish with this slide, quick note on organic nomenclature. Benzene derivatives are one of the most common exceptions to nice systemic nomenclature. Just because it's one of the older molecules in terms of when it was discovered and how long people have been playing with it, it has common names that have just stuck around and are unlikely to go anywhere. So here are the five you should know about. In the upper left-hand corner, we have a methylbenzene, better known as toluene. Beneath that, we have an aminobenzene, better known as aniline. Then in the middle, we have benzaldehyde. That's an aldehyde attached to a benzene ring. Upper right is a benzene alcohol, better known as a phenol or phenol. And then bottom right, we have a carboxylic acid of benzene, benzoic acid. That is all I really want to say about those. We'll cover those pretty well in organic nomenclature. And that is that as far as we're going to cover in this video. When we come back, we will start looking at the different functional groups that we can chuck on to our alkanes.